Reaction mechanism of transition metal complexes to reaction mechanism of square planar complexes. Mechanism of ligand displacement reactions in square planar complexes. The ligand displacement in square planar complexes is much more favorable via the associative pathway than of the dissociative one, which can be explained in terms of low steric crowding due to the lesser coordination number. Consider general ligand displacement in square planar complexes Ma3L plus E to Ma3E plus L. Equation first. Now, if concentration of the entering ligand E is very large, the pseudo first order rate law for reaction first is rate is equal to K1 Ma3L plus K2 into Ma3L into Le. Equation second. Rate is equal to take common Ma3L from K1 plus K2 into E. Rate is equal to take K naught is equal to K1 plus K2 E. Put rate equation rate is equal to K naught into Ma3L. The value of K1 and K2 can be calculated from the intercept and slope of the plot of the observed rate constant Vs versus concentration of E. All type of entering ligands, the values of both K1 and K2 are non-zero, which suggests a possibility of dissociative pathway, solvent assisted SN2 pathway. The non-zero value of K1 can also be interpreted in some other form of the associative pathway in which the solvent molecules also act as the nucleophile and compete with E to form Ma3S, Ma3L plus S2 at constant K1. Remove ligand L and attach with Ma3S. When ligand E reacts with Ma3S, then ligand S remove and Ma3E is formed. Now, as the concentration of the solvent is practically constant, the rate of the reaction depends upon the concentration of Ma3L only and becomes of first order kinetics. Square planar complex when react with the ligand S at slow step, then it forms square pyramidal structure, then after it forms trigonal biopyramidal, and when ligand L is removed then and react with ligand E then forms square pyramidal. This is the reaction mechanism. The systematic mechanism of solvent-assisted ligand displacement reaction in square planar complexes normal SN2 pathway. The non-zero value of K2 can be explained in terms of the normal associative route in which the entering ligand replaces the leaving group via a 5-member transition state Ma3L plus E. At constant K2, ligand L is removed, then Ma3 is formed. It has also been observed that the rate of the direct associative route is generally higher than the rate via solvent assistance. The rate has also been found dependent on the nucleophilicity of the solvent, suggesting a key role of the solvent attack in ligand displacement. This is the mechanism of ligand displacement in square planar complexes via normal associative pathway. Trans effect. The tendency of an already attached group to direct the incoming ligand to its transposition in ligand displacement reactions in square planar complexes is called as the trans effect, and such groups are labeled as the transdirecting ligands. The various ligands have different transdirecting effects, and when these ligands are arranged in increasing order of their trans effect, Cn negative is greater than C2H4 and CH24 greater than CO, then NO, SCN negative, NO2, I negative, Br negative, Cl negative, pyridine, NH3 OH negative H2. This is the increasing order of their trans effect. The trans effect may also be defined as the labelization, means the easier displacement of the ligands trans to other transdirecting ligands. The transdirecting ligands are also called as spectator ligands, as they are neither the entering group nor the leaving group yet affect the rate of ligand substitution. The trans effect may be classified into two types: kinetic trans effect, the trans effect in which certain ligands increases the rate of displacement of the ligands positioned trans to them. Now, as this effect deals with the rate only, it must not be confused with trans influence, which involves a weakening of the trans bond and hence is thermodynamic in nature. If E is the entering ligands, T1 and T2 as the transdirecting groups, K1 and K2 as the rate constant, and L is the leaving group, then when platinum, which is a metal atom, is attached with T1, A, and L, then E1 ligand is react with this. Then ligand L is removed from its position and E is attached at the L position at a constant K1. Similarly, in K2, kinetic trans effect in action with K2 is greater than K1, shown that T2 ligand is having greater trans effect strength than T1. Thermodynamic trans effect, it may be defined as the impact of a ligand on the length of the bond trans to it in the ground state of a square planar complex. Like trans effect, trans influence is also independent of metal ion but primarily upon the geometry of the metal center. Thermodynamic trans effect in action, showing that T2 ligand is having greater trans effect strength than T1. It is clearly that trans bond length is done more profoundly by T1 than T1, T2 than T1, which infer that the thermodynamic trans effect of T2 ligand is higher than T1. Theories of trans effect. The polarization theory. This theory deals with the metal center has a tendency to induce a dipole moment in the surrounding ligands by polarizing them. In case of Ma4 type complexes, type ion induces an equal dipole moment in all the four surrounding ligands, which are in turn cancel out each other due to square planar geometry. In case of Ma3b type complexes, the situation is quite different, as the polarizability of all the four ligands is not anymore the same. If the polarizability of the B type ligand is higher than that of A type, then the primary change of the metal ion will polarize A more effectively. Thus will induce a strong dipole moment in A-type ligand. The dipole moment is also bound to induce an alternate dipole in the metal center also. The orientation of this dipole is such that it repels the negative charge on the ligand A-type situated trans to B. Therefore, according to this concept, the trans effect is directly proportional to the polarizability of the ligand. A structure for Ma4 complexes and B structure for Ma3b complexes. The pi bonding theory. The nature of the trans effect is electronic instead of steric, means that the electronic profile of the ligand is primarily governing trans effect strength of various groups, considering the trans effect of halide ions I negative is greater than Br negative and it is greater than Cl and F negative. It seems that the increasing electronegativity makes them poor sigma donor and sigma base, which in turn also decrease their trans effect strength. Exceptionally, high trans effect of the ligands like CO, C2H4 or PR3 cannot be explained by sigma donation ability, as they are not very good sigma donor by pi acceptor in nature. So we can conclude that a stronger trans effect is the combination of both. Either it should be a strong sigma base or it should show a good pi acid character. Let T be the transdirecting group, L as the leaving group and E as the entering group. The entering ligand binds to 16 sigma platinum 2 complex to form 18 electron complexes, which in turn again converted into a new 16 electron complexes. The mechanism of associative ligand substitution of platinum 2 complexes. Electron transfer reactions. Electron transfer reactions of transition metal complexes are the oxidation reduction reactions which involve the transfer of one electron from one complex to another. The complex which loses electron, the oxidation state of metal increases and it is said to be oxidized, and this complex is called reducing agent. The complex which gains electron, the oxidation state of metal decreases and it is said to be reduced, and this complex is called the oxidizing agent. Example: FeCN6 4 negative plus FeCN6 3 negative. First is reducing agent, means to say reductant, and second is oxidizing agent, means to say oxidant. Then FeCN6 3 negative plus FeCN6 4 negative. Types of electron transfer reactions. The electron transfer reactions involving transition metal complex occur by the following two mechanisms: outer sphere mechanism, inner sphere mechanism. Outer sphere mechanism. In this type of reactions, both complexes participating in the reactions undergo substitution reactions more slowly than the rate of electron transfer. The oxidant and the reductant come to each other, and the transfer of an electron takes place from reductant to oxidant. Silent features of outer sphere mechanism. Both the reactants should be kinetically inert. However, if one of the complexes is labile, then the inert complex should not possess a donor atom which can be used to form the bridge with the labile complex. Example: reduction of FeCN6 3 positive by chromium H2O6 to 2 positive. If both the oxidant and the reductant are labile and there is possibility of electron transfer from pi star of reductant to pi star of oxidant, then the reaction proceeds through outer sphere mechanism. FeH2O6 2 positive plus Fe star H2O6 3 positive to FeH2O6 3 positive plus Fe star H2O6 2 positive. When both the reactants are inert with respect to ligand exchange, example FeCN6 4 negative and FeCN6 3 negative, a close approach of the metal ions is impossible and the electron transfer takes place by a tunneling or outer sphere mechanism. The electron transfer is very fast when both the complexes are low spin, including that the electron transfer takes place from T2G pi star of reductant to the T2G pi star of oxidant, because energy levels of these two T2G orbitals are same. The T2G orbitals are not shielded from the ligands. The rates of electron transfer are much faster between the complexes which have pi acceptor ligands like Cn negative phenyl, because pi acceptor ligands have vacant pi star orbitals that can accept electron being transferred, then pass them to the receiving metal ion oxidant. These reactions are: first is for self-exchange reaction and second is cross reaction. In outer sphere mechanism, bonds are neither broken nor made. Mechanism: FeCN6 4 negative plus FeCN6 3 negative. To form FeCN6 3 negative plus FeCN6 4 negative. FeCN6 4 negative is for low spin, FeCN6 3 negative for low spin. First electronic configuration is T6 2G, T5 2G, and EZ is empty. It is inert in nature. The distance between Fe2 positive and Cn negative distance 195 pm, and for Fe3 positive to Cn distance is 192 pm. More repulsion, therefore CO3 positive negative bond distance is larger than that of CO3 positive NH3. Since T2G orbitals point between the ligands, therefore ML distance do not change appreciably. Therefore, the rate of electron transfer is fast. The ligand Cn negative is pi acceptor, which facilitates the electron tunneling and also it stabilizes complex in lower oxidation state. Thus, electron transfer is fast. Both the complexes are inert and electron transfer is faster than cyanide exchange. Example 2. In cobalt star NH36 3 positive plus CO NH36 2 positive to CO star NH36 2 positive plus CO NH36 3 positive. First is low spin and high spin, second is high spin, and low spin is inert and high spin is labile. Then electronic configuration is T62G empty, and electronic configuration for high spin T52G and EG2. Then bond length between cobalt and NH3 is 193 pm and another is 211 pm. The rate of electron transfer is slow because CONH363 positive is low spin and CONH362 positive is high spin. Low spin CONH363 positive has an electronic configuration T62G with all orbital d electron pointing between the ligands, but the high CONH362 positive has an electronic configuration T52G, E2G and 2EG electrons pointing directly at the ligands. The electron present in EG orbitals cause more repulsion. Therefore, CO3 positive NH3 bond distance is larger than that of CO3 positive NH3. Inner sphere mechanism. The inner sphere electron transfer reaction. The oxidant and reductant share a ligand in their coordination sphere to form a bridged complex. The electron is then transferred through the bridging ligand cobalt NH3 5Cl 2 positive plus CrH2O6 2 positive plus 5S3O positive form SCOH2O6 2 positive plus CrH2O5Cl 2 positive plus 5NH4 positive. Silent features of inner sphere mechanism. One complex reductant is labile and another oxidant is inert. The inert complex must have at least one bridging ligand. In some reactions, the bridging ligand is also transferred from oxidant to reductant, which depends upon the relative stability of the product. Either e.g. sigma star or T2G pi star orbitals of both the reactant participate in electron transfer by inner sphere mechanism. If both the reactant is in an electron transfer reaction involved of same symmetry, the electron transfer will be fast. Inner sphere electron transfer reactions are faster than similar reaction occurring through outer sphere mechanism. The rate of electron transfer increases if the bridging ligand possesses unsaturation mechanism CONH35Cl2 positive plus CrH2O6 2 positive plus 5S3O positive to form COH2O6 2 positive plus CrH2O5 Cl2 positive plus 5NS4 positive. CONH35Cl2 positive is low spin and its configuration is T2G6EZ0 inert in nature, and Cr chromium H2O6 2 positive is high spin and its electronic configuration is T2G3 and EZ1 which is labile in nature, and COH2O6 2 positive which is form high spin and labile, and CrH2O5Cl2 positive is inert in nature. In this reaction, cobalt 3 positive is reduced by chromium 2 positive and the bridging ligand Cl negative is transferred from coordination sphere of cobalt to that of chromium. The electron transfer takes place from EZ of chromium H2O6 2 positive to EG of cobalt NH35Cl2 positive. Thus, electron transfer by inner sphere mechanism is fast. The The chlorine atom of inert CONS35Cl2 positive remains firmly attached to CO3 positive, replace H2O from while CrH2O6 2 positive to form a bridged complex. Electron transfer takes place from chromium 2 positive to cobalt 3 positive through Cl bridge. This step is rate determining step. Now the bridged complex dissociates in such a way that chlorine atom remains attached with chromium. In this reaction we can see in the last step, the 5 coordinate CONS352 positive species picks up water molecule to form CONS35H2O2 positive complex ion, and this complex ion is hydrolyzed to give COH2O6 2 positive ion. This reaction is cobalt NH35 2 positive plus H2O 1 water molecule is added, then cobalt NH3 5 H2O 2 positive, and when 5 hydronium H3O positive is added, then cobalt H2O6 2 positive plus 5 NH4 positive is formed. Rate is equal to K into oxidant into reductant is equal to K into CONS35 Cl 2 positive into chromium H2O6 2 positive. Electron exchange reaction. On the basis of mechanism, the redox reactions of transition metal complexes have been divided into two types, outer sphere and inner sphere. The electron sphere can also be classified on the basis of metal centers involved as the electron transfer between two different oxidation states of same metal ion. These reactions are generally called as self-exchange reaction. The electron transfer between two completely different metal complexes. These reactions are called as cross-section reactions. The electron exchange of or self-exchange reactions may simply be defined as the redox reaction involving the transfer of electron between two complexes having the same ligand and the metal ions but with different oxidation states. The reactants in electron exchange reactions are indistinguishable from the products. These reactions result in no net chemical change and can be studied only by special experimental techniques. FeH2O6 2 positive plus Fe star H2O6 3 positive to form FeH2O6 2 3 positive plus Fe star H2O6 2 positive. Similarly, these cobalt and manganese reactions, all of the above the electron exchange reaction proceeding via the outer sphere electron transfer mechanism. These two graphs are for between reaction coordinates and potential energy. First shows self-exchange and second shows cross-exchange. The comparison of potential energy curves of self-exchange and cross-exchange. After mixing the reactants, the rate at which the radioactivity disappears in M star 3 complex is the rate of electron exchange in two complexes. Similarly, the rate at which the radioactivity appears in the M star 2 complexes oxidation state 2 complexes can also be used to estimate the rate of electron of exchange. Factors affecting of electron transfer rate reaction. Electrostatic repulsion between ions of like charges increases the activation energy, hence the rate of exchange of electron decreases. When there is no exchange in the shapes of molecules, possibility of fast electron transfer always remain. Fast electron transfer take place when due to coupling or by an atomic ligand, electron reaches on the surface of the complex. Generally, in comparison to ligand exchange, electron exchange is fast. The value of rate constant depends upon cation present in the solution. Due to formation of ion pair, activation energy repulsion decreases because the electrostatic repulsion decreases, resulting in increase in the rate. With the increase in the conductivity of the ligand, electron transfer increases. When the difference in the shapes of oxidant and reductant are much high, then there is possibility of slow reaction. Higher is the negative value of del G naught for the reaction, faster is the reaction.